Okay, so we're going to move on to a new unit and we're going to start talking about acids and bases. And so my first question isn't an acid-base question. It goes back to solutions a little bit, but I wanted to remind you of something. What do dilute and concentrated mean? The answer is dilute means we've got a small amount of solute per amount of solvent, and concentrated means a lot of solute per amount of solvent. When you do the worksheet assigned for today, keep that in mind as that concept in mind. Now, scientists have come up with different ways of describing the properties of acids and bases. A scientist named Arrhenius was the first one to come up with the idea. And what he decided is an acid is anything that when you put it in water forms an H plus ion. Bases are anything when you put them in water break apart to form hydroxide ions. Now, this is a pretty limited theory, all right? The reason why it's limited is because, well, guess what? If you don't have any water, there's no way to tell whether you've got an acid or a base. And second, as you'll find out, there are some things which are bases that do not fit this theory. So the theory is sort of a subset of all acids and bases. So what we're really going to talk about is a different theory. Although this was the first one, it was important. The different theory, which was put together by two scientists named Bronsted and Lowry. Now, in the Bronsted-Lowry theory, we look at reactions. So acids give up a hydrogen ion. Bases accept a hydrogen ion. Now you notice I'm writing proton. I want you to think about it. A hydrogen atom is made of a proton and an electron. It has zero charge. A hydrogen ion has lost its electron and gained a plus charge. So the only thing left is a proton. Okay, so that's another reason why we can just refer to it as a proton. Now let's take a look at the Bronsted-Lowry definition in action. So if we react HCl with NaOH, let's look at what happens. So HCl and NaOH form water and sodium chloride. Now remember, Bronsted-Lowry definition, we're trying to look for, let's say, a Bronsted-Lowry acid. Does this gain, the HCl gain or lose a hydrogen? It looks like it gives a hydrogen over here because the OH and the H make water and the Na and Cl make this salt. So the acid, the H plus ion, donates the H plus ion. So this has got to be the acid. The base accepts it. So the OH of the NaOH accepts the hydrogen ion to form water, and so the sodium hydroxide must be the base. Here's another example. Suppose we react water with ammonia. So here's water, here's ammonia. What happens is the ammonia breaks the water apart to make hydroxide ions, and the ammonia gains a hydrogen ion to become ammonium ion. So this is ammonia, this is the ammonium ion, okay? So which is the acid and which is the base? What we do is we look at what happened, okay? Which is the acid and which is the base? The acid loses a hydrogen. It gives it to the other thing. So clearly H2O, which became OH minus, must be the acid in this example. NH3 gains a hydrogen. So NH3 goes to NH4 plus, so it gained a hydrogen, so it must be acting as the base. So those are a couple of ways you can look at the Bronsted-Lowry definition. You can tell what's the acid and the base by what happens in the reaction. Now, strong versus weak. These are a couple of definitions that apply specifically to acids and bases. Strong, what's the definition of a strong acid? It's an acid that completely breaks apart. So if you put HCl in water, what you see is it will form chloride ions and H3O plus, which is called a hydronium ion. 100%. So all of this and all of this go to that, period. So that's a strong acid. So what does weak mean? Well, a weak acid only breaks apart a little bit. So acetic acid is a weak acid. It breaks apart between 1 and 2%. So here you can see this is acetic acid. This is water. Do you notice that the water is gaining a hydrogen from the acetic acid, but only a little bit of it, maybe 2% of the water, of the acetic acids are going to give up a hydrogen to form the hydronium ion. So you get a little bit of the acetate ion and a little bit of hydronium ion, but this is considered weak because it doesn't completely go. The reaction doesn't go 100%. Now, here's the thing. There's tons, thousands of weak acids. There's only 7 strong acids. So what you need to do is you need to memorize the strong acids, because if you're asked what's strong and what's weak, you need to be able to, figure it out. And it's much harder to memorize thousands than it is to remember 7. If you remember the 7, then you know everything else that's an acid is weak. Just remember the 7 strong. So that's by far the easiest way. There's only 7. Hydrochloric acid, hydrobromic acid, hydroiodic acid. Now those are all acids that come from the anion comes from a halogen, which is group 17. There's sulfuric acid, nitric acid, and this is chloric acid and perchloric acid. So all the names are here, okay? These 7 you should commit to memory. If you don't commit it to memory, then you'll have trouble knowing what's strong and what's weak. So it's very, very helpful to be able to sort of memorize this stuff. Now, oxyacids, well, what the heck is an oxyacid? Acids like acetic acid are considered oxyacids, and they are all weak. So oxyacids can be written 2 different ways. For acetic acid, we can write it like this, which is the way you're used to, or we can sort of write it like this, which is a way of showing a chemist how things are connected. These hydrogens are connected to this carbon, these oxygens are connected to that carbon. So that COOH group, this thing, is called a carboxyl group, and if you have that, you're an oxyacid, which by definition means you're weak. So you can see here's what that COOH group looks like, how it's all organized chemically. And over here, you've got this extra CH3 right here attached to the COOH, and that is going to be acetic acid. So there's your ideas, all right? Carboxyl groups are this. Acetic acid is basically a carboxyl group with a methyl group attached, a CH3 attached. Okay, strong versus weak bases. Guess what? It's going to work exactly the same way as strong and weak acids. It turns out there's only a few strong bases. Everything else is weak. So what we do is we memorize the strong ones, and then we don't have to worry about memorizing the weak. We just know anything that isn't strong must be weak. Now, there's a heck of a lot more weak bases than strong bases. So we're going to memorize. Here are your strong bases: lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide. Now, take out a periodic table and look. Look where lithium, sodium, potassium, rubidium, and cesium are. And you will notice that they are all alkali metals. So an alkali metal hydroxide, OH is a hydroxide, those are all strong. So that's 5 of them right there. Now the other 3 are alkaline earth metal hydroxides. So calcium, strontium, and barium are all in the second group. And they are all considered strong bases. Some aren't. Like, for instance, magnesium hydroxide is also an alkaline earth metal hydroxide, and that one is not a strong base. So these are the 8 that you have to memorize. Now, everything else is a weak base. This is ammonia, which you saw earlier, reacting with water, and it gained a hydrogen. So ammonia acts like a weak base. If you put compounds that contain NH2 groups in water, they will also act like ammonia and break water apart, and this will become NH3 with a plus charge. So here is an example. Now, if any of you are Breaking Bad fans, CH3NH2 is actually called methylamine, and it was the compound that was the controlled substance that they were using to make crystal meth out of all things.